All right, so we're going to continue from where we left yesterday on chapter 5, normal probabilities. And we're going to begin with exercise 5. A survey indicates that people use their cellular phones on average of 1.5 years. So that's the mean. Before buying a new one, the standard deviation is 0.25. So that's sigma. A cellular phone user is selected at random. What's the probability that the user will use their current phone for less than 1 year before buying a new one? Assume that the variable is normally distributed. Well, if it's not normally distributed, we couldn't do it anyway. So he wants, guys, the probability that X, not Z, it's just say a user. He's not talking about Z. If he's talking about Z, he will put Z. But if he's talking about Z, he wouldn't give you a mean and a standard deviation other than 0 and 1. So the question is, guys, if you select a phone user at random, what is the chance that this person will replace his or her phone before 1 year of buying this phone? I don't think many of us do that they only use the phone for less than 1 year and replace it with a new one. So let's see what the probability is. I think the probability is going to be low, and let's check. They say on average, people keep their phone for 1.5 years with a standard deviation of 0.25. So that's normal, CDF. Okay, I need your help, guys. Now tell me, what's the lower bound here?
Minus a million.
Minus a million, comma, 1, comma, 1.5, comma, 0.25. And you guys take a few seconds to compute this together. Okay. Let me do it. I hope that you're using your calculator. You can't just watch me doing the thing, guys. It will, I mean, yeah, it will make sense to you, but you need to do the real practice, especially when you do your homework or take the quiz or test. And that's a 1, comma, 1.5, comma, 125, close. And here you go, 0.0228 for decimal places. Good, we're getting more students today, I'm happy. Let's change it to a percent, guys. Here's a question for you. Do you think it is usual to find a person that uses his phone for less than 1 year?
No.
No. Why? How can you explain to someone that it's not usual?
The percent is really low.
Yes, less than 5%. Means unusual, guys. Yeah, that's how you can determine whether an event is usual or unusual. It goes below 5%, it's unlikely to happen. Okay, next exercise. You're gonna see, guys, I'm gonna be redundant to just using normal CDF in many of the exercises. A survey indicates for each trip to the supermarket, a shopper spends an average of 45 minutes. Once you see the word average, guys, you know this is the mean. With a standard deviation of 12 minutes, that's sigma. The length of time spent at the store is bell-shaped. Normally distributed means bell-shaped. If it is not bell-shaped, we couldn't proceed with this exercise because all the math I'm teaching you now is based on the population being normally distributed, bell-curved, and is represented by the variable X. A shoppers enter the store. What is the probability that the shopper spends at the store between 24 and 54 minutes? That should be easy, guys. In my guided notebook, I left a blank here, so you put the 24 and then 54. So that should be what? Normal CDF. 24, 54. Then mean is 45. And standard deviation is 12, guys. Lower bound, upper bound, mean, standard deviation. Okay, let's do the calculation. Second, distribute, normal CDF, 24, comma, here's a comma, guys, you can see it. Then 54, comma, then 45, comma, then 12. This is important information for the manager to know how much people are spending at the store so they can decide how much staff they need to put on the floor. All right, so enter 0.7333. Before I continue, I would just want to address one thing. For example, in this question, guys, if you didn't have technology and you only had a table to do this problem, how would you do it? You would have to change the 1 to a z-score. Then you have to do z equals 1 minus 1.5, which is the mean, divided by the standard deviation, which is 0.25, and then use table 4 to locate the probability. And it will turn out to be 0.0228. But so you can save this step if you have technology. You don't need to do it at all. You just use your calculator. And I'm fine with that. Just so you can appreciate, this calculator. Find the probability that the shopper will spend on the store more than 39 minutes. So just put more than 39. Okay, guys, help me out here. Normal CDF. Lower bound. We see
39.
39.
And then negative 1 million.
No, what goes after 39 has to be a large number. So not negative a million, it will be what?
54.
Million. Remember, this is how it looks like. Let me sketch this one, guys.
Don't we use the input for the one that's above it?
No. That's a separate question. This is the mean. This is this is 45. This is the 39 right here, somewhere here. And he wants it greater than 39, guys. Can you see this? So it goes, remember, always greater than. When you do always a greater than, the upper bound is a million or trillion or whatever you want. But when you do a less than, you begin with a negative a million. Let's make it, just this is a common practice. So A and B have nothing to do with each other. They're totally separate questions. And then 45 and then 12. Unless if the store says, I'll tell you what could have worked. How many hours does the store open? Let's say 8 hours. Yeah, you can put 8 hours of time there. It's gonna work because nobody will stay a million minutes, at the store. That's why I told you it's exaggerated here, but it's always to be safe and put a very large number. So it's gonna work. Even if you put 500 here, it's gonna work because nobody stays at the store 500. A shopper wouldn't go and stay about 8 hours, at the store. Never heard of that. Okay, let's do it. You're ready? So normal CDF. I'm gonna try the 500, guys, and show you that you're gonna get the same answer. Second, distribute. Normal CDF. Okay. 39 minutes, comma, a million, comma, 45, comma, 12. The answer is 0.6915. Let's do it with other than a million. Let's do 500 or 1,000. You will get the same answer, guys. Watch. Second in variables. Normal CDF. Okay, 39 minutes, comma. Just 1,000, comma, 45, comma, 12. See, it's the exact same answer. If I put 500, it will be the exact same answer, 6115. Okay. Here is a question for you now. If 200 shoppers enter the store, how many of them would you expect that will be in the store for more than 39 minutes? We already answered the probability that a shopper will spend more than 39 minutes at the store, which is 69%. Now the question is, if 200 enter the store, how many of them will you expect to spend more than 39 minutes at the store? Any ideas? It relates to B, guys. You're gonna need, just the answer from part B. Does it help to find probability of X greater than 39 first? Yes. We need to know the chance that a shopper will spend, one shopper will spend more than 39. And we already done that. It's 0.6915. What do I do to find how many shoppers? Will be. Any ideas? This is not a probability question anymore. It's common algebra, math question. If you know the percent, guys, and you want to figure out how many of the 200 will spend more than 39. If I tell you 69% of my students get an A, and I have 40 students, how many will they get an A? You just take the 69% and multiply by 40. And it's the same here. So this is what you do, guys. 0.6915, just multiply by 200. Yes, 200 shoppers. Let's see. Times 200. 138. We're gonna round this one. We can't have a fraction of a shopper. Any questions? We're good? All right, we'll move to the next one. One more exercise, practicing normal probability. An easy exercise as well. Triglycerides are a type of fat in the bloodstream. The mean triglyceride level in the United States is 134. So the mean, guys, or the average is mu here, which is 134. Assume that triglyceride levels of the population of the United States are normally distributed with a standard deviation of 35. That's sigma. You randomly select a person in the United States. What is the probability that the person's triglyceride level is less than 80? Okay, I'll hide this, guys, and tell me how do I do this on the calculator. So what goes in first? Normal CDF. We're gonna have to access the formula.
Would it be the negative 1 million?
100%. That's what I've been trying to say. And then what? 80. And then the mean. Look, the third argument is the mean, and the fourth is the standard deviation. Always, always, always. 35. So let's see what's the likelihood you find someone at random in the United States with a triglyceride level less than 80, which is very good if your triglyceride is less than 80. Okay. I'll use the newer calculator now. You can see my camera now, it's projecting. There you go. So we're gonna go second, variables, normal CDF, negative a million already there, 80. What was the average? 134. And the standard deviation is 25. 0.0154. Oh, 35. I made a mistake here. I put 25 for the standard deviation. Let's do it again. Negative 80. You can see I made sigma should be 35. 0.0614. Now, if he asks you to this as a percent, just change it to a percent, guys. So if the question is what percent, just it's a probability, just change it to a percent. It's 6.14%. So remember, guys, area under the curve. It's the same as a probability. It's the same as what percent. They all refer to the same thing, but different wording. If he asks you to find area under the curve, he wants a probability. If he asks you what percent of people in the United States have triglyceride less than 80, he wants the probability. And if he asks you probability, it's a straightforward probability question. So this is how we use the normal CDF function to compute normal probabilities given the mean and the standard deviation. One formula that does it all for sections 1 and 2 and chapter 5. Now I'm gonna move to section 3, which is not difficult. There will be a new formula introduced, and then we'll move, just to the core of this chapter of this book, which is section 5.4. I'm gonna demonstrate 5.4 using an applet online in a few minutes. So let me just do section 3 now. So if you're taking notes, if you have this, guys, this marks the beginning of section 5.3 here. Okay. What I've been giving you an X value right here, less than 80, and ask you to find a probability. In section 5.3, we're gonna reverse the work. We're gonna give you the probability, and then we're gonna ask you to go back and find the original X value, if possible. So it's a reverse work, going backwards. And there is a formula, rather than using normal CDF that will find the probability for you, there is another formula, or you can use the table to go backwards and find the actual X value. So let me give you an example of what I'm talking about here. Watch here. Finding value is given a probability. In the previous section, you were given a normally distributed random variable X, and you were asked to find the probability. In this section, you will be given a probability, and you'll be asked to find the value of the random variable X. Here's one. Find the Z-scores that corresponds to an area, a cumulative area of 3.3632. So look, guys, you have the area, which is 0.3632. I want to find this Z value right here. Let me put the table on the screen. I don't want you to look at the other one. Because they already give you a hint of what's happening, but okay. How would I use the table to find the z-scores? He gives me the area. Remember, guys, the areas are inside, and the z-scores are on the outside, right here. He gave me an area of 0.36, what was it? I forgot. 3632. How can I find the z-score that corresponds to this?
You find the decimal on the chart and then whatever z-score lines up with.
Exactly. And look, this is the 3632. I see it right here. And you guys, can you help me read the z-score that corresponds to this area? There you go. Watch, guys. There's a 0.06 here, and there is a negative 0.3. So what would the z-score, guys, be? Negative 0.3, and then what? 5, I'm sorry. So it's negative 0.35. That would be the z-score. This is how you can do it using the table. But there is also a better way, guys, to do this, which I'm going to show you instead of using the table. So let me show you what he did here. Okay, watch. He located the 0.362, and he's telling you, look, read it from here. It's negative 0.35. Now, a question for you guys. Why did I pick, the page that has the positive z-scores, not the negative z-score, not the positive ones? I knew right away it's going to be negative. How did I know that? I didn't look at the one that with positive z-scores.
Because it's on the left side.
Why? How do you know? What's the area here? Read it for me. If the area is less than 50%, it must be negative. If it is more than 50%, it must be positive right away. And look, it's clear here. You see he's marking z below 0, so you need to do the negative. But even if it doesn't give you the graph, it is negative z-score when the area is less than 50%, a positive z-score when the area is more than 50%. And when it is exactly 50%, we know what the z-score is. It's always 0. Okay. Let's do exercise 9 and show you how to do this. And I will show you how to use the calculator for this. A vet records the weights of cats treated at a clinic. The weights are normally distributed with the mean of 9 pounds. So mu is 9, guys, and a standard deviation of 2. What is the value x corresponding to z-scores of 1.96, negative 0.44, and 0? So there are these 3 z-scores, and I want to find the 3 x values. Well, here's the formula for z, guys. If I give you the value and the mean and the standard deviation, you can find z. But now he's giving you z, and he wants you to find x. Look what we can do. We're going to do some algebra to give you a formula for x. Do a cross multiplication, guys. So you get x minus mean equals z times sigma. And then to solve for x, guys, you just add a mu to both sides. So there's a formula for x. Okay, so let me do it for 1.96. X will be, z is 1.96, guys. Sigma is 2 plus the mean, which is 9. And you just use your calculator to do the math. 1.96 times 2 plus 9, 12.92. This is the first one. Let's do it for negative 0.44. What's x? It will be negative 0.44. So what he's trying to tell you guys, if you have z, you know how to find x, the raw value. So knowing z, that means we know x times 2 plus 9. Okay, and that will be 8.12. And for the final one, guys, for z equals 0, x is going to be the mean. It will be 0 times 2 plus 9, which is 9. As I told you, when z is 0, the value is the mean itself. So that's 9. I said here, let's us write a formula for x. I already did. And this is the formula for x. All right. You would like to know how we can find this z value using the calculator. So I'm ready to show you this. So if you have the area to the left of the target, how do you find the value of the target, just where the area ends at? So we need to find z. Here's how we do it on the calculator. Watch. I'll do it on both, using both calculators. So let me do it on the first one here. You go to second and variables. You see what comes after normal CDF? INV. Does anyone know what INV stand for here? Can you guess? It should be an easy guess, guys. Inverse, yeah. Exactly, Diva. It's the inverse process of the normal CDF. I agree. So you just click on it. He wants the area. He gave us the area to the left, which is 0.3632. Since we're working with z-scores, you keep it at 0 and 1. We're keeping it at 0 and 1. And then paste. I'm done. And negative 0.35, guys. Exactly what we got off the table. If you round it to 2 decimal places, it will be exactly negative 0.35. We will do some more of this, but this is inverse norm. So, or using TI-84, Z equals inverse norm. You put area to the left, and then 0, and then 1. So you got 0.3632, comma 0, comma 1, and we got the answer. Now let me do this using the other calculator, guys. Clear the screen. Second, distribute, inverse norm. Okay, area. We need the area to the left of our target, which is 0.3632. And then comma. There's the comma again, guys. 0, comma 1. There you go. Exact same answer. We're going to use the calculator for the next exercise. Exercise 10. Scores for the California Peace Officer Standards Training Test are normally distributed with a mean of 50 and standard deviation of 10. An agency will only hire applicants with scores in the top 10%. What is the lowest score you can earn and still be eligible to be hired by the agency? So we have a mean, which is 50. We have a standard deviation, which is 10. And let me draw a sketch, guys, top 10%. This is the mean. This is X now, guys, because he's not working with Z. He's not giving me Z values. The mean is 50. Okay. Let me ask you a question, guys. where would the top 10% be shaded, to the right or to the left? You need to know that. This is very, very important because your answer, that can decide whether your answer is going to be correct or wrong. The top 10% would be located on the right tail of the curve or the left tail of the curve. Can I get some feedback from someone? What do you guys think?
On the right?
On the right, top 10% has to be on the right because it's the top scorers, the one who get high scores. High scores, as you move to the right, the scores get higher. So this is it. And this is the 10% right here. We need to know the score right here, guys. This is the person right there in the top 90%, 10%. I need to know the X value. That's what's missing. All right, okay. How am I gonna do that? We're gonna use an inverse norm for this. Okay, and please bear with me and pay attention. So that will be inverse norm. Let me write down the details and then we'll apply the calculator. Okay. The inverse norm, guys, requires that you put the area to the left of the target. This is my target. It does require the area to the left. So what is the area to the left of this target right here?
90%.
Excellent. It is 90%. If you have the area to the right, you don't put the area to the right. The formula is, whomever designed the formula, he designed it, just with area to the left in mind. So if this is 10%, guys, that will be 90%. And even if you put 10%, guys, you're going to get an answer that doesn't make sense, which I'll explain to you in a little bit why it doesn't make sense. And we're almost done. What's the mean? 50. And the standard deviation, what was it? 10. You don't put 0, 1 here because we're doing X, we're not doing Z. So let's do that. Enter. Okay, let me go to inverse norm. Sorry, we got quit, clear, second, and distribute, and inverse norm is number 3. So actually, guys, in chapter 5, you only use number 2 and 3. Area, 0.90. Now, some of you, if they have even a newer calculator than this, they might have an option at the bottom. You let me know later and I'll tell you how to use that. It says left, right, and middle. If this is the case, let me know, guys. In this case, you can put the area to the left, which is 10, and then at the bottom say it's a left area, and then it will still pick it up. Mean is 50. Standard deviation is 10. And I got 62.8. If it is a whole number, guys, so anyone who scores 63 and up will be hired by the agency. Any scores lower than 62.8 will not be hired by the agency because they want the top 10%. So the top 10%, the lowest score in the top 10%, guys, will be 63. So anything that is 63 and higher will be accepted and will be hired by the agency. Okay, that's what top 10%. Now, let's say a students make a mistake and instead of putting 90%, they put 10%. I'm going to show you what happens. And you tell me what's wrong with the answer. .10, 50, 10, paste. It says 37. So anyone who gets 37 and up will be higher. That doesn't make sense. Why, guys? That's a wrong answer. You know what this says? That anyone below average will be higher. What's the average here? The average is 50, as you can see right here. So how could someone be a top 10% candidate and his score is less than the average? That doesn't make any sense, guys. So then where your answer is below average, you know that your answer was wrong. But if the question about the lower 10% for something else, yeah, that will be a 37, the answer. But he's asking about top 10%. So that's why the answer has to be more than the average. So this is how exercise 10 works. Okay. One more thing, just 1 second. Okay, so this is the handout you received from me by email today. We're going to do number 10. It's section 5.3. Scores on the set form a normal distribution with mean of 500 and standard deviation of 100. What's the minimum score necessary to be in the top 15% of set scores? There you go, guys. Here's a sketch. When it comes to scores to be in the top 15%, you have to be on the right. That's 15%. And you're here. So we want this value. Can you guys help me out how to do it? We use an inverse norm. You don't need to use the table if you know how, if you understand how to use the inverse norm formula. So what would be the area to the left, guys, of your target?
85%.
Exactly. And put 0.85, guys. And then put 500 and put 100. If you put 15, you'll get a score less than 500. That doesn't make any sense. Let me just use the other calculator so you can have a flavor of both. Trust me, guys, using the calculator is going to save you tons of time. So even if the problem in the homework online, he shows you an example done by hand, you don't have to follow this. Just use the calculator. You're going to get the same results. Since set scores, guys, are rounded to the nearest whole number, so I would say it's 604. Okay.
Just a question. Do you have to put 0.85 into the you have to put like the point or the 0 point?
No, not need. No need. Just 0.85 will do it. Okay. Yep. Next one, part B. Find the range of values that define the middle 80% of the distribution of set scores. Okay. Let me sketch this one and show you the middle 80%. Middle 80%, that means 80% right here in the middle. That's the 80%. He wants, guys, this value. Let's call it X1, and he wants that value, which is X2. The mean is still 500, and the standard deviation is still 100. Okay, who can help me find those values using the calculator? You might have 1 or 2 exercises in the homework with middle 80% or middle 60% or middle 90%. So you're gonna have a chance to learn how to do this. If this is 80% right here, guys, what's left for the tails?
10%.
10%, yes. I agree. You have to split them up because that's a middle. Okay, what is X1? I'll start. Inverse norm. What's the area to the left of the target X1? Can you guys agree with me? It's 10%, just a 10%. 0.1, and then put 500, and then put 100. What about X2? Will be inverse norm. What's the area to the left of X2? It's the complement of 10%, not 80. There's more than 80. This is 80 and extends all the way. So there will be what?
90.
90%. Look, guys, here's the hint. If this is 10%, the rest of the 100 will be here. So that will be 0.9, 500, and then 100. And then you can use your calculator. You can use the calculator to find the answers. Okay, that is about inverse norm. Okay, here's another practice. I would like to do this one also 9, and then we'll move to the last section, 5.4. The Welcher Adult Intelligence Test Scale is composed of a number of subsets. On one subset, the raw scores have a mean of 35 and a standard deviation of 6. Assuming that the scores form a normal distribution, it's always this assumption, guys. So you have a mean of 35 and a standard deviation of 6. What number represents the 65th percentile, which means what number separates the lower 65% of the distribution? Let me show you a sketch here. What do we mean by that? Okay. You know, the middle is the 50%, so 65% of the data is right here. This is the 65%, and he wants this number, X. That is what, so when he gives you a percentile, he's giving you the area to the left, guys. So in order to do it, you simply just go X equals inverse norm and put a percentile. And make sure to put the percentile as a decimal. So it will be 0.65, and the mean is 35, and the standard deviation is 6. So let's find this number. So again, when you're given a percentile, don't ask yourself, is this a left or right? It's always a left, so just use it straightforward. .65, mean is 35, standard deviation is 6, 37.3. He might ask you to round your answer to 1 decimal or no decimals. So that's what number represents the 90th percentile. Same thing, guys. I'm not going to sketch it now since you know what to do with percentile. Just put the 0.90, then put the 35, and then put the 6 here. And that would be, I'm going to use the other calculator. That's faster actually, because one less window to worry about. 0.9, comma, and then 35, comma. Again, the comma is right there, guys. 6. 42.7. Okay, this is number 9 is a mixture between section 2 and 3, guys. Now he's asking you what is the probability. He's not asking you for a number again, so he's going to give you numbers. So we're back to section 5.2. What is the probability of getting a raw score between 28 and 38? So you just do it like this. Okay, can you guys remind me of the formula we use here? What formula do we use to find a probability? What is it called? Normal CDF. 28, watch. 38, mean is 35, and then 6. I'm not gonna do it. I think you should have a grasp of how to use the normal CDF now. What is the probability of getting a raw score between 41 and 44? Same thing. Normal CDF 41, 44, 35, and 6. All right, so that's how the first two parts of this question, guys, were section 5.3. And then I just put those two sections back to show you that I can ask questions. So any question that asks you to find a probability is a normal CDF. Any question to ask an X value or a number or a Z score, it is an inverse norm that we covered in section 5.3. Okay, now I would like you guys to give me your attention. I'm just gonna stop sharing and share a different screen with you to demonstrate section 5.4. So just give me a minute. Okay. So what you see now is an applet that I'm gonna use to demonstrate section 5.4, which is the central limit theorem. When you work with data, guys, you collect samples. We work with samples. We usually don't work with the entire population. We don't work with one individual. As you can see, all the problems that I did in section 5.1 and 5.2, we select one problem, one person at random, and then we find a probability. What's the probability of X being less than this? What's the probability of X being more, X in between? It's always about one item, one quantity, but that's not how samples work. Samples, you have to pick a decent sample size. If your population is large, probably you need, a larger sample size. There are times where you pick a sample size, but we will be working with samples. In real life, it's all about samples. What I'm going to show you, if anything, it changes as we shift to samples. With the rules that I introduced in section 5.1 to 5.3 still apply, or there will be some slight changes. I just want to bring to your attention one thing. A sample size, statisticians consider a sample size of 30 or more to be large, and anything less than 30 is considered low. This applet doesn't have the number 30, but it has the number 25 instead. So when I use the number 25, guys, please assume just like I'm using the number 30. It's going to work pretty much the same thing. So I'm going to demonstrate this applet, and I'm going to ask you, please pay attention and tell me what you observe. So let's begin using this applet. You guys agree with me that the population that we have is bell-shaped. It's a normally distributed population. Okay, I'm gonna pick some samples of size 10. So the sample has a size 10. So 10 items will be in the sample. Here's what I'm gonna ask the applet to do. I'm gonna ask the applet to pick 100,000 samples for me of size 10 and find the mean of each sample. So how many means would the applet calculate for me if I pick 100,000 samples, guys? Would you agree that it's gonna do 100,000 means? But this is all gonna happen in a blink of an eye in the background, guys. And then I'm gonna ask the calculator to do a histogram or a graph of all those data from the samples. And I want you to compare, the two graphs with the original one and the new one. The original graph, look at the original graph, guys. It has a mean of 16 and it has a standard deviation of 5, as you can see here. Watch carefully and see what's gonna happen. So let me show you how the samples are animated. So I'll just animate a sample and watch how the calculator, how the program does this. It picked 10 pieces of data and then it's going to put the sample. What the program did, it picked 10 members at random from the sample, from the population, and then add them up, divide by 10, and found, the sample mean. This is 1, but we're going to go beyond 1, guys. We're going to do 100,000 sample. Let me do a 10,000 sample. What the program did, guys, already collected 10,000 samples of size 10 each, computed the means of each one. So it did it 10,000 times and graphed all those means. I want to do 100,000 now. All right. Do we want another 100,000? Just click of a mouse. There you go. We got, guys, 310,001 sample graphed there. Any observations? This, the blue is for the samples. The black is for the original population. So the black one is for X and the blue one is for X bar, which is the sample means. I would like you guys to tell me if you notice any similarities between the two. And if yes, what are they? Please look and don't be shy of participating. I'll correct you if you make mistakes. What do you observe? Look here and there.
They have the same mean.
Yes, very good. They have the same mean. So if you work with samples, guys, you will get the population mean. You notice, guys, the mean is 16 and the mean is 16. What else do you observe? There's another similarity, guys. Look at the shapes.
They're both bell-shaped.
They're both bell-shaped. Very good. So the sample means, you know, are bell-shaped as well. Now there is a difference here. Look at it.
The standard deviation gets smaller.
Excellent. The standard deviation gets narrower. And this is a good thing for a statistician, for us to work, because when the standard deviation is small, that means we have more consistency. That's why we tend to work with samples rather than working with the population, because you get a smaller standard deviation. Smaller standard deviation means your accuracy level is going to be high and you're going to be more consistent in your results. Now, I would like you guys to look at this. This is 5. What is the standard deviation here? 1.58. You see, it's smaller. That's why you see a narrower curve, guys. You see the same mean, a narrower curve with smaller standard deviation. Now, there is a relationship between 5 and 1.58. Actually, I didn't need to run the applet to figure out the 1.58. So here's what I'm gonna ask you to do. Get your calculator ready. Take the original standard deviation 5 and divide it by square root of 10, because I used a sample size of 10. So divide 5 by square root of 10, guys, and tell me what you get. I'm gonna do the same thing as well. And you're gonna be surprised. Do I have some answers?
1.58.
1.58. So you could figure out, you know, the standard deviation without running the applet. We know the mean remains the same, which is 16, but the standard deviation becomes smaller, and the relationship is the new standard deviation of the sample means is the original population standard deviation divided by the square root of the sample size. Okay, let me change now the sample, guys, to 25. And which I like you to assume it's 30 or more. Okay, let's do an animation. It's gonna pick 25, guys, count. This is only one sample mean, and then it's gonna graph the sample for us. There you go. Now, let me do 10,000 sample. Another 10,000, another 10,000. Okay, that's 30,000. Okay. What do you guys agree with me that the mean remains the mean? It's 16 and 16. It could be 15.99, which is okay. It's still pretty much the same. Now, guys, I would like you to take 5 and divide it by square root of 25. What would you get? Yeah, the median is also the same. I had a student say same median, yes.
You get
Okay.
5.
So if you get 5, guys, and divide it by square root of 25, do you agree with me that you will get 1? Because square root of 25 is 5. So it is 1. All right. Now, watch this. I'm gonna change this from normal to Scoot, not normal population. And remember, guys, all the work we've been doing based on normal population. So this is not normal. This Scoot to the right. What's the mean here? 8.08, and the standard deviation is 6.22. Please pay attention. We're going to take samples, large samples of size 25 or more, and I'm going to do 10,000 of those. What do you notice, guys? The population is not bell-shaped. Remember, original population is not bell-shaped. Do you notice the mean remains the mean of the sample means? It's 8.08 and 8.08. What's the shape of the sample means? Is it skewed to the right or it's bell-shaped? What do you notice of the blue shape?
Bell-shaped.
Bell-shaped. So that's good because we can work with bell-shaped distributions. So even if your original population is not bell-shaped, the sample means the X bars are bell-shaped. And guys, I like you to take the standard deviation, which is 6.22 and divided by square root of 25. You should get 1.25, which is already there. Okay. Now let me just make a custom population. If you ask me what's the shape of this population, I'll tell you I don't know, it's just custom population. And let's get, what's the mean? 18.58. Watch, guys. Let's get 10,000 sample. Another 10,000. That's 20,000. What's the mean of the sample means? These are called the sample means. It is 18.58, as you notice. The standard deviation, guys, take 8.91 and divide it by square root of 25, which is 5. Let me do that and see if we're lucky, we're going to get 1.77 or close to it. It doesn't have to be exactly, but close to it. Yeah, I got 1.78, which is extremely close. So the conclusion, guys, regardless of what the population is, whether normally distributed or not, if you use a large sample size, you're always going to get a normal population that have the same mean, and where the standard deviation of the sample means equal the original standard deviation divided by the square root of the sample size. This is called the central limit theorem, and we're going to show you how to use this one in an exercise before we wrap this up. So I'm going to go back and share the camera screen and write some results out of our observations. So we'll stop sharing here and we'll go there. Okay. Let me just go back. Right here. All right. So sampling distribution of the sample means, I said, watch the simulation demonstrated in class in Zoom carefully, then write your observation. Let's write some stuff together, guys. Sampling distribution is the probability distribution of a sample statistic, mainly X bar. So we're working with the means. It is formed when samples of size n are repeatedly taken from a population, and that's what we did. If mean is the original population mean, mean of X bar is the mean of the sample means, which has turned out to be the same, guys. If sigma is the original population standard deviation, sorry here, standard deviation, that's a mistake. Then sigma X bar is standard deviation of sample means. Okay, and let's write the results here from the applet observation. The mean of the sample means is equal to the mean. Mu of X bar, as you notice, guys, it's the same as the mean. The standard deviation of the sample means is equal to the population standard deviation divided by square root of n.
Excuse me, is this a different worksheet?
No, that's a continuation.
Oh,
You don't have this?
oh, never mind. Okay.
Found it? Okay.
Yeah, thank
That's
you.
probably the last page.
Yeah.
When the original population, guys, is not normally distributed, just like this, the last one I did, guys, then the distribution of the sample means is normally distributed. Normally distributed means bell curved, guys, bell shaped. If the sample size is 30 or more, although I demonstrated 25, it works, but the standard is 30 or more. Look, guys, that was the original population. And then we got population of sample means, which is bell-shaped. The mean is the same as the mean, but the standard deviation is a lot smaller. So this relates to that, and that relates to that. Okay. Let me show you exercise 11 and how to use the central limit theorem. So the central limit theorem, guys, is this. Mu of x bar is the same as the mean of the original population, and sigma of x bar is the same as the original sigma, but divided by square root of n. So when you work with samples, guys, you use the same mean as the population mean, but when it comes to standard deviation, you need to change your standard deviation to sigma divided by square root of n instead of sigma. That's the only difference. I will demonstrate that in an example, and we'll wrap this up. Cellular phone bills for residents of a city have a mean of 63 and a standard deviation of 11. So mean is 63 and standard deviation is 11. Random samples of 100. You see now we're going beyond 1. That's n. Cellular phone bills are drawn from the population and the mean of each sample is determined. Find the mean and the standard error of the mean of the sample in distribution. Okay, then the mean, he wants the mean of x bar. We know it is the same as the original mean. So it will be what, guys? $63. Now the standard error of the mean means the standard deviation of the sample means, which is sigma of x bars. It will be what? Sigma divided by square root of n. And sigma, what did he give us? Sigma to be 11 divided by square root of 100, which is 11 over 10, which is 1.1. So sigma of x bar, guys, is called the standard, if you see it in the book, standard error of the mean, or a standard deviation of the sample means. So it is 1.1. You notice, guys, that supports what we did. You had a large 11 standard deviation when you work with the population. When you work with samples, look what your standard deviation is. It's only 1.1. Okay. And we're gonna do one exercise to show you how to use the normal CDF function. Let's do that, one more exercise. From the book. All right, there you go. '37, lumber cutter. It's on page 272. The length of lumber a machine cuts are normally distributed with the mean of 69 inches and a standard deviation of 0.5 inches. So you got mean of 69 and a standard deviation of 0.9. Let's write it down here. Number 37. Okay. Mean is, what was it? I'll write it down, 96. And sigma is 0.5. Okay. First question. What's the probability that a randomly selected board cut by the machine has a length greater than 96.25 inches? One board, guys, has nothing to do with the central limit theorem. Central limit theorem is about samples. So it's one, it's just back to section 5.2. So he really here wants the probability of X more than 96.25 inches. Can you guys help me do this using what we learned? It will be what? Normal CDF. Okay, what's the lower bound here? Any feedback, input? I know how to do it myself.
Is it negative a million?
No, it's a greater than. It's a greater than, so you start with what? 96.25, then you put a million, and then you put 96, and then you put 0.5. So this is section 5.2, guys, is still, but you will see the next question that we're gonna do. So let me do this one. If you go to normal CDF and input those four values, 96.25, a million, and then 96, and then 0.5, you will get 0.3085. Okay, part B, guys, which is the part that we just did. So let me go to part B and then we'll wrap this up. You randomly select 40 boards. So what's N here? N is 40. We're not working with one item anymore, we're working with 40. What is the probability that their mean length is greater than 96.25? So he's asking about the probability of the sample mean. And look, how do you write this, guys? That's the big difference between what you did in part A and this one. Instead of putting X, he's asking about the sample mean. So you put X bar greater than 96.25. This is the main difference between the two sections, all the sections and section 5.4. It will be normal CDF, watch. 96.25 is the lower bound. 1 million is the upper bound. The mean remains the mean, 96. And who can tell me what's going to change here? The only thing that's going to change here is the standard deviation. What do I put for standard deviation, guys? 0.5, and then what? What did we say sigma of X bar equals? It's sigma divided by square root of N. So square root of 40. That is the big difference. So he's asking you about the probability of the sample mean. So instead of X, you use X bar. And instead of sigma, you just put sigma over square root of N, and everything else remains the same. And let me do this using the calculator. It should be it for this lesson. So I'm gonna go normal CDF. Okay, and let's do this right here. Okay, lower is 96.25, upper is a million, mean remains the same. The only thing that's changing, guys, is the standard deviation. Watch, you can put it here. 0.5 divided by square root of 40. And here you go, paste. Okay, it's 7.827 E negative 4. Don't ignore E negative 4. It means you have to move the decimal place 4 digits to the left. So it would be 0.0008. There you go. So that is the answer. So the difference, guys, finally, between working with one item and working with a sample of size n bigger than 1 is that your standard deviation will change. You have to use the original standard deviation and divide it by the square root of the sample size. How do you know that he wants you to do that? He will be asking you what's the probability that the mean or the sample. You can see in 37, guys, he said, what is the probability that they have a mean length? Mean means X bar greater than 96.25. Okay. That is everything in section 5.4. This afternoon, I will be available, guys, if you show up, and I'll work on the activity that I emailed to you, so just do some more practice. There will be an assignment for 4 and 5. 5 also will be a very short assignment. I will send you some details this afternoon in how to submit both assignments, and I will include both assignments as well. And after today also, guys, the worksheet, the practice sheet that I made available this morning, I will work out the solutions to the exercise and PDF and send them to you so it can assist you as you complete those 2 chapters. All right, guys, so I'm gonna stop sharing and you're all set.